You ever notice how some things just happen? Like an ice cube always melts in a warm room, right? But you'll never see a puddle of water just decide to freeze itself back into a cube. Or how a drop of ink spreads out in a glass of water, but it never ever gathers itself back into a perfect little drop. Well, there's a reason for that. There's a fundamental rule of the universe at play here, and today we're going to unpack it.
So let's get right to the heart of it. Why do some things happen all by themselves, spontaneously, with zero outside help? What's the hidden force deciding which way things are going to go? It kind of feels like nature is a one-way street for a lot of these changes, and the answer to why that is, it all comes down to a concept called entropy.
So, here's our game plan. We're going to build this up step by step. First, we'll figure out what entropy even is. Then, we'll see how you can actually measure it. We'll touch on a really key property it has, something called a state function. And then, we'll connect it all back to why things happen spontaneously. And finally, we'll look at the ultimate tool scientists use for this, which is called Gibbs energy.
Okay, so first stop on our journey. Let's get to know the star of the show, entropy. What in the world is it?
You know, at its heart, entropy, which we represent with the letter S, is just a fancy scientific way of measuring chaos. That's it. It's a number that tells you how much disorder or randomness there is among the molecules in any given system. Think about it like this. You have a brand new, perfectly ordered deck of cards that has low entropy. Now, throw that deck of cards up in the air. The scattered mess on the floor, that has way, way higher entropy. It's just a measure of disorder.
All right, so knowing what it is, that's one thing. But this is science, right? We love to measure things. So how do we actually put a number on this change in disorder?
Well, the formula for the change in entropy is actually pretty straightforward. It's the amount of heat you supply to a system divided by the temperature at which you supply it. Now, that little rev on the cue just means we're measuring the heat in a really specific way, super slowly, and a perfectly reversible, efficient process. It's just a way for scientists to get a clean, standard measurement every time.
And the units we use for this are joules per Kelvin. So what does that actually mean? Well, you can think of it as telling you how much the disorder ramps up for every single degree of temperature, fueled by a certain amount of energy in joules. It's a really elegant way to put a number on chaos.
Now, entropy has this really cool property, a kind of superpower, that makes it so useful for scientists. It's what's known as a state function, and that's just a technical way of saying it doesn't care about the journey.
All it cares about is the starting point and the finishing point. The path you took to get from A to B, totally irrelevant. Imagine you're climbing a mountain. Your total change in elevation is exactly the same whether you took the short, super steep trail or the long, winding, scenic route. The only thing that matters is the difference in height between the base and the summit. Entropy works just like that.
Okay, here we go. This is the big one. This is where it all comes together. We're finally ready to connect this idea of entropy directly back to our original question. What makes something happen all on its own?
And here is the absolute key insight. To figure out if something will happen spontaneously, you can't just look at the thing itself. You have to look at its effect on the entire universe. So for our ice cube to melt, that's our system. It has to pull in heat from the room around it, that's the surroundings. The total change in entropy is the sum of what happens to the ice cube plus what happens to the room. You have to look at the whole picture.
And this, right here, is the unbreakable, non-negotiable law of the universe. For any process to happen on its own, the total entropy of the universe has to go up. The overall disorder of everything must increase. If the total change is zero, well then nothing happens. The system is in a perfect standoff, what scientists call equilibrium.
Now, you might be thinking, trying to calculate the entropy change for the entire universe every single time sounds a little bit difficult. And you'd be right. Thankfully, a super brilliant scientist named Gibbs came up with a much more convenient tool that basically packages this universal law into one single easy-to-use value. This tool is called Gibbs free energy, or delta G, and it's an absolutely genius shortcut. It takes that total entropy change of the universe and bundles it into one number that's just about our system. You see, it's directly linked to the total entropy change, but notice that negative sign. That cleverly flips the script, and it makes predicting whether something will happen incredibly simple.
So here's the final rulebook. Because of that negative sign, a process is spontaneous only when the change in Gibbs energy, delta G, is negative. A negative delta G means the universe's disorder is going up, and nature gives it a green light. If delta G is positive, it's non-spontaneous. It's just not going to happen on its own. And if delta G is zero, we're at that perfect balance point again. equilibrium.
So the big takeaway here is that spontaneous change, the direction of time itself, really, is driven by this unstoppable, irreversible increase in the total disorder of the universe. Which leaves us with one last really big question to chew on. If the universe's natural tendency is always towards more randomness and more chaos, then how on earth is something as complex, as structured, and as beautifully ordered as life itself even possible?